Vacuum energy is an underlying background energy that exists in space throughout the entire universe. One contribution to the vacuum energy may be from virtual particles, which are thought to be particle pairs that blink into existence and then annihilate in a time span too short to observe. They are expected to do this everywhere throughout the universe. Their behavior is codified in Heisenberg's energy-time uncertainty principle. Still, the exact effect of such fleeting bits of energy is difficult to quantify. The effects of vacuum energy can be experimentally observed in various phenomena such as spontaneous emission, the Casimir effect and the Lamb shift, and are thought to influence the behavior of the universe on cosmological scales. Using the upper limit of the cosmological constant, the vacuum energy of free space has been estimated to be 10⁻⁹ joules per cubic meter. However, in both quantum electrodynamics and stochastic electrodynamics, consistency with the principle of Lorentz covariance and with the magnitude of the Planck constant requires it to have a much larger value of 10,113 joules per cubic meter. This huge discrepancy is known as the vacuum catastrophe. Origin. Quantum field theory states that all fundamental fields, such as the electromagnetic field, must be quantized at each and every point in space. A field in physics may be envisioned as if space were filled with interconnected vibrating balls and springs, and the strength of the field were like the displacement of a ball from its rest position. The theory requires vibrations in, or more accurately changes in the strength of, such a field to propagate as per the appropriate wave equation for the particular field in question. The second quantization of quantum field theory requires that each such ball-spring combination be quantized, that is, that the strength of the field be quantized at each point in space. Canonically, if the field at each point in space is a simple harmonic oscillator, its quantization places a quantum harmonic oscillator at each point. Excitations of the field correspond to the elementary particles of particle physics. Thus, according to the theory, even the vacuum has a vastly complex structure, and all calculations of quantum field theory must be made in relation to this model of the vacuum. The theory considers vacuum to implicitly have the same properties as a particle, such as spin or polarization in the case of light, energy, and so on. According to the theory, most of these properties cancel out on average, leaving the vacuum empty in the literal sense of the word. One important exception, however, is the vacuum energy or the vacuum expectation value of the energy. The quantization of a simple harmonic oscillator requires the lowest possible energy, or zero-point energy of such an oscillator to be. Summing over all possible oscillators at all points in space gives an infinite quantity. To remove this infinity, one may argue that only differences in energy are physically measurable, much as the concept of potential energy has been treated in classical mechanics for centuries. This argument is the underpinning of the theory of renormalization. In all practical calculations, this is how the infinity is handled. Vacuum energy can also be thought of in terms of virtual particles which are created and destroyed out of the vacuum. However, these particles and antiparticles may interact with others before disappearing, a process which can be mapped using Feynman diagrams. Note that this method of computing vacuum energy is mathematically equivalent to having a quantum harmonic oscillator at each point and, therefore, suffers the same renormalization problems. Additional contributions to the vacuum energy come from spontaneous symmetry breaking in quantum field theory. Implications. Vacuum energy has a number of consequences. In 1948, Dutch physicists Hendrik B. G. Casimir and Dirk Polder predicted the existence of a tiny attractive force between closely placed metal plates due to resonances in the vacuum energy in the space between them. This is now known as the Casimir effect and has since been extensively experimentally verified. It is therefore believed that the vacuum energy is real, in the same sense that more familiar conceptual objects such as electrons, magnetic fields, etc. are real. However, alternate explanations for the Casimir effect have since been proposed. Other predictions are harder to verify. Vacuum fluctuations are always created as particle-antiparticle pairs. The creation of these virtual particles near the event horizon of a black hole has been hypothesized by physicist Stephen Hawking to be a mechanism for the eventual evaporation to black holes. The net energy of the universe remains zero so long as the particle pairs annihilate each other within Planck time. If one of the pair is pulled into the black hole before this, then the other particle becomes real, and energy, mass is essentially radiated into space from the black hole. This loss is cumulative and could result in the black hole's disappearance over time. The time required is dependent on the mass of the black hole but could be on the order of 10,100 years for large solar mass black holes. The vacuum energy also has important consequences for physical cosmology. General relativity predicts that energy is equivalent to mass, and therefore, if the vacuum energy is really there, it should exert a gravitational force. Essentially, a non-zero vacuum energy is expected to contribute to the cosmological constant, which affects the expansion of the universe. In the special case of vacuum energy, general relativity stipulates that the gravitational field is proportional to ρ plus 3p. Quantum theory of the vacuum further stipulates that the pressure of the zero-state vacuum energy is always negative and equal in magnitude to ρ. Thus, the total is ρ plus 3p equals ρ minus 3ρ equals minus 2ρ, a negative value. If indeed, the vacuum ground state has non-zero energy, the calculation implies a repulsive gravitational field, giving rise to acceleration of the expansion of the universe. However, the vacuum energy is mathematically infinite without renormalization, which is based on the assumption that we can only measure energy in a relative sense, which is not true if we can observe it indirectly via the cosmological constant. The existence of vacuum energy is also sometimes used as theoretical justification for the possibility of free energy machines. It has been argued that due to the broken symmetry, free energy does not violate conservation of energy, since the laws of thermodynamics only apply to equilibrium systems. However, consensus amongst physicists is that this is unknown as the nature of vacuum energy remains an unsolved problem. In particular, the second law of thermodynamics is unaffected by the existence of vacuum energy. However, in stochastic electrodynamics, the energy density is taken to be a classical random noise wave field which consists of real electromagnetic noise waves propagating isotropically in all directions. The energy in such a wave field would seem to be accessible, e.g., with nothing more complicated than a directional coupler. The most obvious difficulty appears to be the spectral distribution of the energy, which compatibility with Lorentz invariance requires to take the form kF3, where k is a constant and f denotes frequency. It follows that the energy and momentum flux in this wave field only becomes significant at extremely short wavelengths where directional coupler technology is currently lacking. History. In 1934, Georges Lemaitre used an unusual perfect fluid equation of state to interpret the cosmological constant is due to vacuum energy. In 1948, the Casimir effect provided the first experimental verification of the existence of vacuum energy. In 1957, Li and Yang proved the concepts of broken symmetry and parity violation, for which they won the Nobel Prize. In 1973, Edward Tryon proposed the zero-energy universe hypothesis, that the universe may be a large-scale quantum mechanical vacuum fluctuation where positive mass energy is balanced by negative gravitational potential energy. During the 1980s, there were many attempts to relate the fields that generate the vacuum energy to specific fields that were predicted by attempts of grand unification theory and to use observations of the universe to confirm one or another version.